Hello everyone, welcome to my presentation. I'm Guiyang from University of Edinburgh. I'm going to introduce our raw paper, Robust Footstep Planning and LQR Control for Dynamic Quadrupedal Locomotion. We know that when a quadrupedal robot is started walking, the floating base is fully constrained. But when the robot is trotting, the system becomes underactivated. We tackle the underactivation problem from both motion planning and control. In the motion planning part, we use a MPC subject to linear inverted pendulum model to generate the optimal footholds. The linear inverted pendulum model decouples the x and y axis motions, and it has analytical solutions. Then we can use the analytical solution to predict the center mass states. We formulate the MPC as a QP with a cost function aiming to track the desired heading velocities. By solving the QP, we can generate the optimal ZMPs for n steps. We only use the first optimal ZMP to map the desired footholds. The ZMP is set to be the midpoint of the supporting line. Considering the heading angle, we can use the geometric relationship to compute the desired foot placements. Then we can use cubic splines to interpolate the swing trajectories. To generate the center mass trajectory, we just need to substitute the first optimal ZMP to the inverted pendulum dynamics. Then we can realize simultaneously heading and turning. So, what about trotting on inclined terrains? We can use the same formulation for x and y directions in this case. But we need to generate the desired center mass position along that axis. In blind walking, by knowing the foot positions, we keep the relative distance to be a constant value between the ZMP and the center mass position along that direction. We can see that the robot still has the push recovery ability on a slope. Now, let's look at our trajectory tracking controller. We keep using our projected inverse dynamic control framework. In this framework, the inverse dynamics is projected into two orthogonal subspaces, constrained free space and constrained space. We do the trajectory tracking in a constrained free space, while a QP is used to satisfy all the inequality constraints in the constrained space. The QP will penalize the trajectory tracking torques if they violate the physical feasibility. In this paper, we replace the impedance control for the base with the LQR controller. The LQR will generate better feedback gains than manually tuned diagonal gain matrices. Here is the dynamic equation in the constraint free space. We can transform the joint space dynamics into task space dynamics. Then we linearize the task space dynamics around the current state. The LQR will generate the optimal feedback gain matrix for this linearized system with respect to the base state. The LQR will benefit balance control. We can see the swing phase can be longer than before after using the LQR controller. Also, we demonstrate our controller can satisfy inequality constraints such as friction cooling constraints. We also introduce this adaptive foot. This foot will benefit the robot while walking on rough terrains. But in this paper, the controller didn't consider the degrees of freedom of the passive ankle. Now, let's look at our experiments. Benefiting from the fast footstep planning MPC, the robot can resist kicking and regulate back. Although our controller didn't consider the passive ankles, it did work in the real robot experiments. It proves the robustness of our controller to model errors. We also took the robot outside the lab and worked it in the campus. But to be honest, the state estimator is a problem without using vision perception. We could achieve better performance with a better state estimator. Here we can see the adaptive foot works well on such rough terrains. Okay, here are the conclusions and the future work. The MPC and the LQR effectively contribute to the robustness of the system. The PIDC control framework covers the shortness of traditional LQR in terms of inequality constraints. We achieved 1.2 meter per second trotting speed in simulation and 0.6 meter per second in real experiments. Future work will make the controller to take the passive ankles into consideration. Also, we will extend the controller to handle gaze with flight face. Thank you for your listening.